Okay, so here's where we were last time. We were talking about linear transformations. So quick reminder, we've actually seen several linear transformations already. We've talked about this linearity property in the past, but we just never quite got around to defining it as a linear transformation. The rationale there is that rather than give you a bunch of formalities at the very start of the course and not be clear on what they're good for or what they do, to start with, getting our hands dirty and actually looking at actual things, and then we'll, define the abstractions, later on. So that's what happened. Okay, so we defined linear transformations, looked at some equivalent formulations, talked about lingo a little bit of what I like to call math slang, right? Be on the lookout for that. Anytime you see the word linear, there's a function somewhere in the conversation. Identify what that is. Somebody is telling you that that's a linear transformation. Okay. Etc. So, and then we talked about how to brute force check that something is a linear transformation. So, again, what you have to do is show that when you put a linear combination in, that you get the expected linear combination out. Okay. All right. So that's where we left off last time. One last quick example before we get to a longer list of examples. The purpose of this next example is just to point out that you can't just assume that everything in sight is a linear transformation. This is a course in linear algebra, sure. It may be that most of the functions that we see will be linear transformations, but that's not a logical basis for inferring that something actually is. So point out, here's a perfectly good function. Nothing wrong with that as a function. I can easily confirm that this value of the function, and I can easily confirm that value is 1, and therefore this equation is true. Thing about it is, if this were a linear transformation, these two things should be equal. But they aren't. So therefore, this is not a linear transformation. It does not satisfy the linearity condition. Now, a quick observation I'll make. Students sometimes get confused. How come, proof by example works here, whereas here we couldn't do an example. Here we had to actually show all the algebra. And it's because if you're trying to show that something is always true, that's hard. That requires algebra. If you're trying to show that something is not always true, then all you're really trying to do is show that it's sometimes false, right? And showing that something is sometimes false is satisfied with a single example. So this is an asymmetric situation, and the way we address these questions is sort of correspondingly asymmetric. Okay. All right. Now I'm going to show you some more examples of linear transformations. This next one looks a little bit weird. For one thing, it's a linear transformation defined on vector spaces of functions. And there's something right off the bat unsatisfying about this. This D, A comma B, right? This domain here, this is an infinite dimensional vector space. Right? You can't visualize what that looks like. It's very upsetting in some sense, right? Likewise, the target, infinite dimensional vector space. So that's weird enough. The linear transformation that I'm also calling D, because this is the book's notation, and I just want to be consistent with the book here. This D, it's a familiar process. D says just take a derivative of whatever function from the domain you put into D. So, said differently, this linear transformation is the act of differentiation. And so my claim is that this is a linear transformation. Now, when I was young, and a lot of students, y'all, at the same stage that I was, are uncomfortable with the suggestion that derivatives are linear. Right? Because you think back to Calc 1 and you think, no, they aren't. The derivative of sine x is cosine x. Cosine x is clearly not linear. So what gives here? So let me clarify. What we are talking about is not I am not asserting that this function sitting inside of that vector space, I am not asserting that this is linear. Certainly not. Cosine x is a wonderful counterexample. These are clearly not linear. What we are saying is not that derivatives are linear, but that differentiation as an action that you do to functions, differentiation is the linear transformation. That's what we're talking about. Okay, so make sure to see the distinction there. The act of differentiating takes in a function and spits out a function. A derivative, right, the thing that got spat out, yeah, that's just a regular old, plain old, real number in, real number out function. The derivative is not linear. The differentiation is linear. Okay. All right. Now, how do I know that this act of differentiation is linear? We're going to prove it brute force, just like we did in the last example we talked about last time. We're going to put a linear combination in, and we're going to show that we get the expected linear combination out. See, I mean, we'll go through the details in a moment. But notice all we have done is just directly brute force check the condition is satisfied. Linear combination in, linear combination out. Okay, so how do we get this done? Step one, with a linear combination put in, plug into the definition. All right, there it is. There's the definition of D. Next, remember some old Calc 1 facts about differentiation. We already know a bunch of stuff about differentiation. I've kind of combined two Calc 1 facts about differentiation into this next step. First thing that we know is we know that when you take a derivative of a sum of two functions, you get the sum of the individual derivatives. Again, ancient history, Calc 1, long since established knowledge. Next, when you're taking a derivative of a constant times a function, you get the constant times the derivative of that function. Again, old news, right? That's something that y'all learned about differentiation way back in Calc 1. So those two facts together, or you might say just, old Calc 1 methods, just to summarize, tell us that this is equal to that. And then we're basically done. You have to observe finally that is the definition of D of F1, and this is the definition of D of F2. And now we are in fact done. And as required, linear combination in, linear combination out. So, good. Okay. Everybody on board? Let me point out while we're here, the argument that we've made to prove that differentiation is linear actually shows explicitly the distinction I'm talking about between differentiation and, derivatives, right? So note the linear combination that I put in here. I'm not putting in a linear combination of like values of x or something, right? If I were going to try to assert that cosine x were linear, I would have to put in some linear combination of x's, some linear combination of the inputs to that function, which is not what we're doing. And we're not doing it because that's not what we're talking about, right? So anyway, you can see right here that we're talking about the act of differentiation on functions because I'm taking a linear combination of functions and checking that you get the appropriate linear combination out. Okay. All righty. Next example. As I'm going to do for a bunch of examples today, I'm going to let y'all prove this one. It's the same strategy. I'm claiming here that when you make a function with a matrix, like we did way back in chapter 1, right? A long time ago. We first did this when we were talking about determinants. When you make a function out of a matrix, that function is a linear transformation. So, way you're going to prove this, way you're going to prove that that is a linear transformation is you're going to put into it a linear combination of vectors in, and then you're going to, compute from the definition and apply a bunch of previously known facts about matrix algebra and get down to the appropriate expected linear combination out. So the details are a little different from the previous example, but structurally it's the same. Different use of past knowledge, matrix algebra instead of Calc 1, but morally, strategically, same proof. So give that a try. Make sure that you can do that. It'd be a great practice problem. Okay, here's another one. Here, let me zoom, focus better. So this is a linear transformation. Now let's walk through exactly what am I talking about here. What I'm claiming is a linear transformation. This thing called S. The formula for which is down here. Now notice this thing called S takes as its input a C infinity function. So a function from that domain is the input, and then what comes out is a number computed by that formula. Okay, so function in, number out, and the value of that number is computed by, well, an integral. So how do we think about this linear transformation? This linear transformation, now don't make the classic mistake that, like you might have when we're talking about differentiation of thinking that I'm somehow claiming that antiderivatives are always linear functions of x. It's not what we're talking about at all. I'm not saying this is a linear function of x. I'm saying that the act of turning functions into numbers by way of this formula, that action is a linear transformation. Note that what this action does is compute an integral. So you might say, if you want to slang this, if you want to translate this statement into English, this is saying that integration is linear. The process of integration is linear on the input functions. Okay. All right, I'm going to let y'all prove this one as well. I'm going to prove something similar to it. I'm going to prove that this is a linear transformation. Note the similarity. When you see how I prove this one, then very similar argument to prove the previous. So again, this is kind of sort of an integration. Our function here, our SG, is defined by this following formula. If you give me a C infinity function f, we get an output value in R1 by way of this formula. Okay, so we're given a function f. The f goes here, but wait a second, I can't compute this without g. What is this g? G is part of my function. Right? So this is not something you can do just arbitrarily to functions f. We have to choose and fix some function called g. With that function called g, I have here a linear transformation SG. Right? And applying SG to f, g being established, is done by that formula. Okay, and I claim that this is a linear transformation. By the way, you might call this, if g is a positive function, you might call it a weighted integration, because you can think of g as attributing different weights to different locations between a and b. Okay, so how do I know that this is a linear transformation? Well, here's the proof. I wrote this out previously to save us a little bit of time. Step 1. Put a linear combination in. Preview, I hope to find that I get the expected linear combination out. Linear combination in, linear combination out. Okay. All right, so from there, with this linear combination being put in, there's the definition of what that function SG does to that input linear combination. Notice here, my input linear combination just goes there per the formula for SG. Okay. Oh, let's see here. How am I going to get rid of that thing? There we go. So next, what am I going to do about this, I'm actually going to do a fair amount of just algebra, plain old algebra. Let me zoom in for visualizing purposes. Here we go. Good old plain old algebra. That's what that is. I'm just distributing the G. No tricky curves there. Next, here I have an integral of a sum. Calc 2 tells me, or actually Calc 1 maybe, tells us that an integral of a sum is a sum of two separate integrals. Calc 1 tells me that if I have a constant inside of an integral, I can factor that outside of the integral. Again, ancient history, old news, right? We're just manipulating out these objects. And so now I have turned this into this. And we're actually kind of done at this point. We just have to sort of realize that we're done. Keep in mind my goal was to get down to here, and notice that is the definition of SG of F1, and this is the definition of SG of F2. And so as desired, we get the expected linear combination out. So weighted integrations are linear transformations. So check by way of this argument. How are we doing? Is everybody on board? Let me take a pause. No questions? Yes?
So the logical hypothesis like both of these proofs can be trying to put into that final form down there.
Yeah. That. I mean, notice all we're doing is we're just appealing directly to the definition of a linear transformation. Here we go. Linear combination in, and I've just got to decide, do I or do I not get the expected linear combination out? So yeah, it's always, we're just directly brute force checking the condition. Yeah. I say always. The examples that I'm showing you here do it that way. There are some instances where you can prove something's a linear transformation in different ways, but this is the sort of the immediate, the direct way to do it. Yeah. Okay. Right. Okay. Let's see here. Next one. So there's several examples that I can show you. Here's another one. This just says when you plug in x equals 0, that's a linear transformation. Notice if you give me a function, right? The output value is a number computed that by that formula. What I have done to that function to get that output number is plug in x equals 0. Okay. So my assertion that this is a linear transformation says that plugging in x equals 0 is a linear transformation, or plugging in x equals 0 is a linear process. And let y'all prove that one. Again, the notation for all of these is a little bit different. The past knowledge that you have to invoke to get from start to finish, a little bit different every time. So I think it's a healthy exercise to do a certain number of these on your own. I think this would be a great one. Give it a try. And but structurally, it's just like all the others we've done. Okay. A little quick cultural note. I wish I had more time to talk about this in class. But there are some really interesting questions about how you can interpret this as kind of that this linear transformation delta naught can be thought of as a kind of a function on its own in a way. And people like to talk about the Dirac delta function. Y'all ever heard of the Dirac delta function? Show of hands, just curious? No? Well, you will. So you'll see it in Math 353. And in a way, the Dirac delta function's kind of a function, but also kind of not, in some weird ways. Anyway, if you're curious, I used to include this as part of Math 216, and over the years, I've made tough choices about what we do and don't have time for, and this, I'm sorry to say, didn't make the cut, but it's a really interesting conversation. If you're curious, ask me in office hours. I would be very happy to give you 15 minutes on how this works and what's interesting about it. Okay. A variation of that. Here, note again, function goes in Real number comes out, real number computed by this formula. This is the act of, to a function, we take several derivatives and then plug in x equals a. And here's the thing, we've already talked about how the act of taking derivatives is linear. Previously we talked about the observation that plugging in x equals 0 is linear. Probably not too surprising. There's nothing magic about 0 in that example. Plugging in any fixed given value of x, also linear. So I don't think this is a surprising fact. Nevertheless, the proof, you're going to write down some slightly different things. So another good practice problem. Okay, old news. In section 4.1, we talked about how the left side of a differential equation that we called L, just as kind of a shorthand, right? We talked about how you can kind of interpret that as a sort of a function. That L, linear differential operator, would take a Cn function and turn it into some output continuous function. And we talked about how that L had a property of linearity, kind of like the linearity that we'd seen at different points in the past. Okay, here it is again. Now I just have the language set up where I can say what I meant by that was L is a linear transformation from this vector space to that vector space. It's not a new statement. It's the same statement from chapter 4, just said in different language. Okay. All right. There's a mishmash of miscellany that we have to talk about for the rest of this section. It's a bunch of important things that just have to, we have to observe and define and check. So here we go. First, we have a nice theorem. It's an unexpected but very interesting theorem, I think, and that is if you have a basis for your domain, okay, so sitting inside of your domain there, you have a basis. If you know what the images are, now keep in mind when we say images mean the outputs that come out of those input values. So the images live in there. They live inside of W. If you know the images of a basis, if you know what T does to a basis for your domain, amazingly, you actually, by virtue of that, by virtue of that, you know everything there is to know about that linear transformation. It's really, really surprising fact. Let me say this in a slightly different way. Keep in mind that a vector space has infinitely many elements in it, right? Now we're speculating that we know about a basis. A basis might have only a finite number of, that's just a handful of little vectors. There's infinitely many vectors in your vector space, and I'm saying, let's suppose that I know what T does just to this finite collection of vectors. Knowing just that, I know all the rest of the whole function. Very, very surprising. It's an amazing feature of linear transformations. Here's the proof. It's a very straightforward proof. Suppose that we have a basis, right? Keep in mind, a basis has some nice properties. One of the properties that we know about a basis is that any vector in the vector space can be written as a linear combination of those basis vectors, and furthermore, can be done in a unique way. Namely, there always will be such coefficients, C1 through CK, called the coordinates. Right? And those coordinates, in addition to existing, they're always unique. So this is a property of bases that we established back in section 2.4 or maybe 5. I lose track. I think it was 2.4. The uniqueness of representation, you might say, bases have the property that every vector can be uniquely represented in terms of coordinates by virtue of this theorem. Okay, so how does this help me? I'm asserting that I know all the values of the linear transformation. I'm claiming that I can compute T of V for any vector V. Here's how I'm going to do it. This vector V, write it as a linear combination, just like we observed that we can do. I know for any vector V, it's just a matter of kind of playing some linear combinations games to figure out what these coordinates are. Say the magic word linearity. Linearity of T allows us to take this linear combination on the inside, move that to a linear combination on the outside. And now I just declare victory. So here's the thing. I mean, I was given that I know the images of the basis vectors. So T of V1 through T of Vk, I know all those by assumption. Also, these coordinates, C1 through Ck, I know I can always find those coordinates. So I know these numbers, C1 through Ck. So if you want to compute T of V, right, write it as a linear combination of the basis vectors, identify those coordinates, plug into this formula, and that's T of V. How are we doing? Everybody on board? So this is a remarkable theorem. The moral that I like to take from this theorem is that when you say that a function is linear, you're saying a tremendous amount about that function. You're saying so much about the function that simply only knowing a handful of values of it allows you to deduce all of the other values. So linearity is a tremendously powerful property for a function to have. Again, I think this theorem underscores that very nicely. Quick example. So here's a linear transformation from R2 to R3. Notice that this pair of vectors 1, 1 and 1, 2, I claim form a basis for R2. By the way, let's think through. How do we know that's true? How do I know that 1, 1 and 1, 2 forms a basis for R2? Well, that's two vectors in a two-dimensional vector space. So the count is correct. So that's part one, right? How do I know that they're not dependent? Well, 2 is a wonderful number. If they were dependent, one of them would be a multiple of the other. That's obviously not true. They're not multiples of each other, therefore they're independent, and a pair of independent vectors in a two-dimensional vector space basis. Old dimension theorem from section 2.4. Is everybody on board with that? Everybody remember that argument? Okay. So I know the images of a basis. And I claim that therefore I know everything else about this function. Suppose you want to know, t of 3, 4. How am I going to figure out t of 3, 4? Well, 3, 4. Oh, let's see here. I need 3, 4 is a linear combination of those basis vectors, like that. Now, I mean, you've got to do a little bit of work to figure out these coefficients of 2 and 1, right? But nevertheless, there is a way to do this. The coefficients are 2 and 1, and then linearity allows me to rewrite like that, just like in our proof above. That's that. That's that. And therefore, the thing that I'm interested in is a little bit of arithmetic, which turns out to be this. And this is always going to work, right? If you want to find t of 76, 143. Well, you're going to have to do a little bit of effort to figure out what the appropriate coefficients are. That's just a chapter 1 problem, linear algebra problem, to solve for those coefficients, and linear combinations give you the answer. Okay. All right. Okay, next item in our list of miscellanea. We define a new object called the kernel of a linear transformation. The kernel of a linear transformation is the collection of vectors in the domain for which the image is 0. An easy starter example. Suppose we look at the linear transformation defined by a matrix. Now again, I go back to this a lot because, this is one of our first linear transformations that we ever talked about. Again, we didn't use the term, but this is an easy linear transformation to talk about. Very familiar linear transformation. And notice the kernel, the collection of all vectors that make this transformation 0. Well, the transformation's computed by this matrix. So really what we're asking for here is, what is the collection of x's that make ax equal to 0? Namely, it's the null space of the matrix. Yeah. So it's a very familiar concept. The kernel of a linear transformation defined by a matrix is just the null space. Recall also, we've already observed the null space is what, way back in chapter 1, we referred to as the set of homogeneous solutions. So 3 different terminologies for the same thing here, which brings up the obvious question, why have 3 terminologies if they're all the same thing? And, there's a pretty good answer to this question, by the way. That homogeneous solutions is a reference to a system of equations. We can choose to view a system of equations with a matrix, but matrices also come from other places. So we have to have a terminology in reference to matrices because they're different things. Matrices can be thought of as linear transformations, but linear transformations also can come from other places and need not be represented by a matrix. To have come from a matrix. So again, we have to have a different terminology to refer to this more broadly defined thing. Okay. All right, how are we doing? Is everybody on board so far? Okay. Here's a hands dirty example. Let's look at this function here. Let me write out explicitly what this function does. This function t of xyz, well, just plug in xyz, multiply by that matrix that's got a lot of zeros in it, and what you end up with is x, y, 0. And with that formula, I can persuade you, I hope, that what this function does is it projects points down or maybe up into the xy plane. Right, for any point x, y, z, just kind of blank out that z coordinate, make it 0. You're going to get the point in the xy plane immediately below or immediately above the input point. All right, everybody on board? Okay, what's the kernel of this linear transformation? The kernel, what are the vectors that when you project to the x-axis, when you project into the xy plane, that give you 0, right? Well, easy sell, it's the z-axis. Points on the z-axis, and only points on the z-axis, when you project to the xy plane, give you the origin. Okay, so that's the kernel. Everybody on board? Didn't color code well there. There we go. Okay. All right. Another familiar example. Again, this is old news, but we've talked about this thing L from chapter 4. We talked about it in chapter 4 as being a linear differential operator. We're now interpreting it as a linear transformation. Same thing. So what is the kernel of this L linear transformation? Well, kernel says, what can I put into it to give me 0? That's the definition of a kernel. What are these things that you put into this linear transformation to give you 0? We've seen this equation before. The way we described this equation back in chapter 4 was, what are the solutions to the differential equation, the homogeneous differential equation? So in this case, when you're talking about a linear differential operator, kernel means homogeneous solutions. Okay, so again, it is familiar example. Okay, new thing to talk about. Something called the image. Well, not really new. So we've talked about images before. Remember the very first thing we did in Chapter 5 was to talk about terminology of objects as relates to functions. And I distinguished between the target of a function versus the image. The target is a space that the outputs have to land in. The image is the actual collection of actual outputs, right, which can be smaller. Okay. All right. So note our definition here. The image is the collection of vectors in the target that actually are outputs of actual input vectors. Okay. All right. So now there is a familiar version of this. Recall that when we first defined kernels and we looked at matrices, the familiar punchline was that, in the case of matrices, kernels are just null spaces. Okay. So there's something kind of like that that's going to happen with images. Thinking of transformations that come from matrices. Takes a little bit more work to get there. But here we go. The image is the collection of all of these outputs. The outputs are computed by that formula. Section 1.2 of the book, Matrix Multiplication, tells us that you can view that as all possible linear combinations of the column vectors. You all recall, this is one of my favorite points of view on matrix multiplication. Forget about that whole row dot column thing. I mean, don't forget it, but try to file that row dot column point of view. Figure prominently in your view of matrix multiplication that you're taking linear combinations of, in this case, columns of the left matrix. Okay, so that being said, the image is the collection of all outputs. The image is the collection then of all linear combinations of column vectors. And where have we heard that phrase before? All linear combinations of column vectors. That's the column space. So, as it turns out, nice point of view. I think this is a great way to think of, why should we ever care about the column space? I never really gave you a very good answer to that question back in Chapter 2. We talked about what the column space was. We talked about how to find a basis for it. And I made some vague references to how it's going to come up in the future. And here it is. So why should you care about a column space? It's the image of that matrix viewed as a linear transformation. An image is a very natural thing. So therefore, column space is a very natural thing. Okay. Alrighty. Let's go back to our previous example. Oh, let me remind you. Here's our previous example, talking about that matrix function there. Right? We agreed that the kernel is the z-axis. Remember, we've got this formula here. Everything goes into the xy, the nearest point in the xy plane. So let's think it through. What is the image of this function? Well, everything that goes into this function comes out in the xy plane. I claim the image is the xy plane. Yeah. Here's the xy plane. XY plane is the image. And our previous result up here said that should be the column space. That should be the span of the column vectors. Well, here's my previous column vectors. Right, the matrix that we had from the previous page, the column vectors are 1, 0, 0, 0, 1, 0, 0, 0, 0. Those vectors are 1, 0, 0, 0, 1, 0. Notice that those two vectors span the xy plane, just like we talked about, right? And then, thirdly, 0, 0, 0, which doesn't do anything. It doesn't contribute to the span at all. So, as expected, the span of the column vectors gives us the image. Okay, so just an example of that in action. couple more exercises for you guys to work on. I think these are nice exercises. The kernel of a linear transformation is always a subspace of the domain. This is kind of a mashup question. So this involves 5.1 ideas in the form of understanding correctly and being able to manipulate algebraically what is a kernel of something, and then it also requires remembering from section 2.2 what is a subspace and how do you prove that something is a subspace. Right? And we did a bunch of examples of those way back when. So you're going to combine your knowledge of those two ideas to be able to answer this question, to be able to prove this result. I think it's a good practice problem. I encourage everybody to do it. As always, if you have any trouble, come talk to me in office hours. Ask in discussion section. Go to the TA office hours. Ask your study partners, whatever. Second fact, the image of a linear transformation is always a subspace of the target. And again, it's a equivalently mashup problem. It's going to be slightly different algebraic sort of look to the question, but structurally same kind of a question. So 2 really good practice problems. I hope you'll give them a try. In fact, I'll give you a hint. Both of these questions are highly analogous to subspace examples that we have already proved back in Chapter 2. So you might look for what are the Chapter 2 analogous subspaces, and where did we previously already prove that those are subspaces. Okay, all right. All righty. So this is a weird fact here. If you have a linear transformation, and I do have to put an asterisk on this, I need for my domain to be finite dimensional. The theorem doesn't really make any sense if this isn't the case. Notice, you can kind of see this coming. I make reference to the dimension of the domain. It better be finite dimensional. Otherwise, I would have an equation involving infinity, and I don't really know what that means, right? So it better be finite dimensional. Otherwise, this doesn't make any sense. Okay. So with that asterisk, finite dimensional domain, linear transformation, amazing fact, the dimension of the kernel, keep in mind the kernel lives in there, the dimension of the kernel plus the dimension of the image, don't forget the image lives in there. The dimension of the kernel plus the dimension of the image is the dimension of the domain. And the surprising fact about this, so the domain is, again, this over here. The kernel and the domain are kind of in the same world over here, but the image is way over here in this other world. It's very surprising that somehow the dimension of this thing over here would be involved in an equation relating the dimensions of these things over here. Pretty unexpected fact. I'm going to show you how to prove this. First, I'm going to make a reference to, the book proves this, and you can read the book's proof if you like. The book's proof I find to be clunky. It's perfectly rigorous. It's fine. Nothing wrong with that. But it's bulky, I'll say. Notation heavy, tedious. I think you're not going to like it. But give it a look. Who knows? You might like it a lot. I'm going to show you a different proof. Now, my proof has the disadvantage that I'm not going to be able to finish my proof for about a week because it's going to take, there's one fact that we're not going to have the tools for until about a week from now. But when I have that one extra little fact done, the rest of the proof will be complete. And here's the little asterisk that I have to put on my proof. I'm going to claim without proof right now, proof to come next week. Oh, by which, of course, I mean after break. That every linear transformation on a finite dimensional domain can be written as a matrix. Now, this is very far from obvious. It's not obvious. It is, however, true, and I am going to prove this later. So for now, you have sort of two choices on the argument I'm about to show you. You can either just take my word for it. Trust me that the proof of this is coming. We will establish this. Or if you prefer, you can say, I don't like to trust people, and you can choose to view the argument that I'm about to give you as only applying to linear transformations that can be written as matrices. And that's also fine. And then I'll persuade you of the last step later. Okay, so here's the argument. If we can view our transformation as a matrix, then I know what the kernel is. The kernel is the null space. We already talked about that. Right? And by the way, I also know if I'm talking about a matrix transformation, the image is the column space. So if I want to prove something about dimension of kernel plus dimension of image, really I just am trying to prove effectively this analogous fact about the dimension of the null space plus the dimension of the column space, and we already proved this. So that's why I like this point of view. It's easy. Right? We reduce the question to a previously solved problem and celebrate. Right? So, reminder, we know how to compute the dimension of the null space. You row reduce and you look for columns that don't have pivots. We know how to find the dimension of the column space. You row reduce and look for columns that do have pivots. Altogether, you get the number of columns, the dimension of the domain, which is what we have up there, yeah.
On a test, we were asked to prove that top statement, and then we basically just did that proof right there.
Yeah.
Are we able to cite previously proved?
So that would be, it would depend a lot on how the question's phrased on the exam you'd want to come up and ask. If I were to write such a question, I would hope that I would have the presence of mind to anticipate that question and clarify in the phrasing of the question. Keep in mind I have the advantage in a class setting that I know I don't have to tell the entire story all in one sitting, right? And I know you have to listen to what I am going to be saying 2 weeks from now, right? And on an exam, you don't have that luxury. So generally speaking, you want what you write on an exam to be a self-contained thing. And I'm taking advantage of the fact that I have this extra advantage. And by the way, with that in mind, I mean, again, I wouldn't write it would be weird for me to write a question that was expecting you to do this without me directing you very narrowly toward exactly this. Yeah. Right. Okay. All right. Gosh, I'm almost out of time. This last thing, we can actually do this pretty quickly. I do have to remind you, though, about some terminology. These words one-to-one and onto. The pair of which is put together in this one word, bijective. I know all of y'all have had Calc 1 courses. In a Calc 1 course, it's really actually kind of necessary to define an invertible function. And the way you define an invertible function, because you talk about arc sine, arc cosine, and natural log, and stuff like that, right? So in order to really define what it means for a function to be invertible, you have to talk about it being one-to-one and onto. So this idea really should have been covered in a Calc 1 class. My experience with Math 216 is that most of y'all's Calc 1 classes kind of glossed over this stuff. So I'm aware of the fact that y'all might not recall or might not have seen these meanings. So let me tell you what these words mean first. So one-to-one and onto just means that if you have a function with a domain and a target, and this is just for symbolic purposes, and so let's pretend my domain has 3 entries in it, very small domain, and my target has 3 entries. And let me draw an example of what the function might do. The function might, for example, send that input there, and that input there, and maybe that input there, let's just say. Both of these words can be defined in reference to this thing called a preimage. If you look at a point in the target, the preimage is the collection of points in the domain whose output values land on that output point. Okay, so this is called a pre-image right here. So that's the pre-image of that output point. The pre-image of that is that point, and the pre-image of that is empty. Right? There are no points over here in the domain that land on that output value. Okay, so with this idea in mind of what a pre-image is, a function is one-to-one and onto if every point in the target has exactly one point in its pre-image. At least one, at most one, exactly one point. So this function I've drawn here is not one-to-one and onto, and I'm out of time. So I'll pick up here and talk about this more on Friday. See y'all later. Come talk to me after class right now. Yeah. Okay. Alrighty. See y'all later.